All right, so now that we have reviewed a little bit about circles, ellipses, hyperbolas, parabolas, um, and now that we've given their planar descriptions, right, as points in a plane, we can look at a more algebraic idea of conic sections. So we've talked about the fact that algebraically the conic sections are polynomials of degree 2 in two variables, right? So all of the terms are degree 2 or less. If you're just confronted with an equation and you're trying to determine what kind of conic section it is, then here's a good summary, right, to kind of help you out with that. Okay, so first of all, if the equation looks like this, so if you have x minus h squared over something plus y minus k squared over something else equals 1, then that's an ellipse. Okay, now contrast that with a hyperbola, which is like x minus h squared over something minus y minus k squared over something equals 1. So the only difference between an ellipse and a hyperbola is that with an ellipse you're always adding, with a hyperbola you're subtracting. Now, since addition is commutative, right, the order here doesn't matter. You're going to get the same curve no matter which order this comes in. Subtraction is not commutative though, right? So with a hyperbola, if your x group comes first, that's a different graph than if your y group comes first. And in particular, what changes is that if the x group comes first, the hyperbola opens left and right? So it opens up along the x-axis. If the y group comes first, then the hyperbola opens up and down, right? So it opens up along the y-axis. One more thing about ellipses, because you might notice that, wait, where are circles on this list? Well, a circle is just a special kind of ellipse, right? A circle is an ellipse where these two denominators are the same number. And if they're the same number, then you can multiply through by that number to just get the equation for the circle that we're used to seeing, okay? And then finally, the oddball is kind of the parabola. You can tell you have a parabola if you're either squaring x but not y, or if you're squaring y but not x. So you're only squaring one of the variables. So if you're only squaring one of the variables, then it's a parabola. Okay? And just like with the hyperbola, the leading group tells you which way it opens, right? So if y comes first, then it opens up along the y-axis. If x comes first, then it opens up along the x-axis. In every single case, the point hk is important. For ellipses, circles, and hyperbolas, hk is the center. For a parabola, hk is the vertex. And in every single case, h is the coordinate that is attached to your x group, right? Your x group, your x group, your x group. And k is the coordinate that's attached to your y group, right? Y group, y group. Okay? So let's practice identifying conic sections. So we won't be graphing any of these. We'll just identify what they are and some of the information that would be helpful in order to graph it, if we wanted to graph it. So looking at part A here, right away, I see a y group, like a y squared and an x squared, so I know it's not a parabola. And then I see a minus sign in between those two groups, so it's got to be a hyperbola, right? This has to be a hyperbola. Some useful information for graphing this thing would be like the center of the hyperbola. The center is 1, 2. M and N also would be useful, right? M, in this case, M is always the thing you're dividing your x group by. Well, the square root of that thing, right? So square root of 4 is 2. N is what you're dividing the y group by. So square root of 16 is 4. And then finally, for a hyperbola, you need to identify if it opens left or right, or if it opens up and down. In this case, since the y group leads, this one's going to open up. So maybe I'll say opens up and down. Okay, so with that information, you should be able to graph this hyperbola pretty easily. So let's look at the next one. For the next one, we have x minus 1 equals y minus 2 squared. So on this one, I'm squaring my y's, but I'm not squaring my x's. That tells me right off the bat this has to be a parabola. The vertex for the parabola would be a useful thing to have if I wanted to graph this. So the vertex in this case is going to be 1, 2. Oh, just like the center on the hyperbola. Is it going to be 1, 2? It's 1, 2 on all of these, isn't it? Well, anyway, so the vertex here is the point 1, 2. The other thing we want to be able to identify if we're graphing a parabola is which way the parabola opens. In this case, since my x group leads, I know that it's going to open up along the x-axis. Now the question is, does it open left or does it open right? For that, we look at the value of a right here. If a is positive, it opens right. Okay, so this one opens right. Note that it doesn't open left and right. Okay, it's a parabola, so it only opens in one direction. It's not a hyperbola, right? Hyperbolas have kind of two different halves. So this hyperbola is going to open up and down, right? It's going to open in both directions. But a parabola only opens in one direction. This parabola opens right. Okay, so I'll let you pause the video. Okay, go ahead and pause the video. See if you can identify the rest of these conic sections. Okay, I'm just going to go ahead and give my answers now without a ton of explanation. This one's a circle. The center is 1, 2. The radius is 9. Okay. This one's a hyperbola. The center is 1, 2. M is 2. N is 4. So it's almost exactly like part A. But this one opens, since the x group leads, this one's going to open left and right. Ooh, look at how I spelled hyperbola. There's no other L, it's just a hyperbola. Okay, and then this one's an ellipse. Okay, it looks almost identical to part D. The only difference is the sign in the middle, and that makes this one an ellipse. Since it's an ellipse, there's no need to identify which way it opens. It doesn't open, it's a closed loop. Okay? And then finally part F, this one's a parabola. With vertex 1, 2. This one opens up. Okay, so that's that. So if these equations are given to you, I'm going to call these things the graphing forms, right? So these things up here I'm calling the graphing forms. So if you have a conic section that's given to you in graphing form, you should be able to identify it pretty easily. So on a test or a quiz, I'm not going to say, hey, this thing's a hyperbola, graph it. No, I'm just going to say, graph this curve. And it's up to you to know that, oh, it's a hyperbola, or oh, it's a parabola, or oh, it's an ellipse, right? So you've got to be able to identify those things. Okay. So as we saw in the introduction to the chapter, conic sections get their name from a graphical three-dimensional characterization, right? They're the intersections of, like if you put two cones tip to tip, and then you intersect that cone with a plane, then depending on how far the plane tilts, then you get all the different kinds of conic sections, right? In sections 1 and 2, we saw their graphical two-dimensional characterizations. Let's talk about their algebraic characterizations now. So if you're just looking at their equations, right? And in particular, what I'm interested in is the general form. So not the graphing form, but let's say that you're given the conic section in general form like this. How do you tell what kind of conic section it is? Well, for one thing, you're going to have some what we call degenerate cases. And these things happen when you don't actually get a conic section. So for example, note that if A, B, and C, right? So if A, B, and C are all 0, so if these terms are all gone, you just have dx plus ey plus f equals 0. That's just a straight line. Okay, that's just a straight line, which is we call that a degenerate conic section. In fact, there are other ways to get degenerate conics as well. So you know, if all of these values are equal to 0, I mean, then you just get a single point, right? So that's another kind of degenerate conic. I'm not really interested in focusing on what am I saying here? What we do want to. So hold on. There are other ways to get degenerate conics as well, but we won't focus on those too much. Yeah, I'm not interested in like how you get lines and points out of this. What I'm interested in are the actual conic sections itself. So what we do want to focus on is how we would graph a conic section if they're given to us in this format instead of being given to us in their nice graphing form. So in this section, we're going to look at the case when b equals 0. So when this xy term is missing. When the xy term is not missing, things get a little bit more complicated, and we're going to talk about that in the next section. Okay, but for now, we're just going to consider cases when this term is gone. Okay. So when b equals 0, we can convert this general equation into one of the graphing forms that we listed on page 1. And to do this, the way that we do this is we group the x and y terms together, and then we complete the square on each group. Now, it may have been a while since you've completed the square, so I'm going to remind you how this goes. Okay. So let's say that we want to graph this conic section. Just looking at it in the format that it's in this general form, you might be able to tell what it is. I don't know. I know what it is, and we're going to talk about how to tell what it is in this section a little bit later on. But you don't actually need to be able to identify it just by looking at it, as long as you can rewrite it in graphing form, which requires us to again complete the square on each group. So first of all, I'm going to group the x's together, x squared minus 8x. And I'm going to leave some space there so I can complete the square. And then I'm going to group the y's together. So I've got y squared plus 18y. And again, I'm going to leave some space so I can complete the square. And this 48, I'm just going to move that over to the other side. Right? I'm going to subtract it over so that equals negative 48. Now, if I'm thinking about completing the square, the trick for completing the square so maybe let me back up. When we say complete the square, what we mean is we want to rewrite this as a perfect square trinomial. So we want to write a number in here so that when we go to factor this in the next step, it's just going to look like x minus something squared. Right? It's just going to be a binomial times itself. Well, so how do we do that? The trick is that this number right here that we add, it has to be half of this number squared. Okay? So half of negative 8 is negative 4. And negative 4 squared is positive 16. So we're going to add a 16 to complete the square on that group. And of course, we're allowed to do that as long as we add 16 on the right-hand side as well. To the y group, I haven't used this pen. But this is a different color, hopefully. I think it's a green color. There we go. Okay. So for this group, we do the same thing, right? We take half of this. Half of 18 is 9. And then we square that, right? 9 squared is 81. So we're going to add 81 to this group. And again, we're allowed to do that as long as we add 81 over here on this side as well. Okay. Now, we should be able to factor each of these groups as a perfect square binomial, right? In this case, I can see that this is going to be x minus 4 times x minus 4. In other words, it's x minus 4 squared. Right? 4 times 4 is 16. So if you FOIL this part out, you're going to get back here. And same thing with this one. We can say, well, this would have to be y plus 9 squared. And then on the right-hand side, I need to total those things up. So let me get the calculator. We've got negative 48 plus 16 plus 81. That comes out to 49. Now at this stage, we should be able to identify this thing, right? This, we're squaring both groups, so it's not a parabola. We've got a plus sign in the middle, so it's not a hyperbola. This must be an ellipse. And in fact, this is a special kind of ellipse, because if we divide through by 49 to get 1 on the right-hand side, we're gonna be dividing each group by the same number. So really, this is what we call a circle, right? This is a circle. It's a circle with center 4, -9, and radius 7, right? So we can graph this thing now. 2, 3, 4. -9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's the center of the circle. And then the radius is 7. Oh, I might go off the page. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, and 7. Yeah, so it's a little bit off the graph paper. But there you go, right? So there's our circle. So that's that one. Okay, let's do another one. Okay, same deal. If I want to figure out how to graph this thing, I need to complete the square. So I'm going to group the x's. 32x squared minus 512x. And then I've got an 18y squared plus 180y equals negative 2,210. Okay, now before I complete the square on these groups, it's easiest to complete the square if you have a leading coefficient of 1. So I'm going to go ahead and factor out these leading coefficients in each of these groups. So for the x group, I'm going to factor out the 32. I'll be left with x squared minus 512 divided by 32 is 16. So x squared minus 16x. Leave some space to complete the square. Here I'm going to factor out the 18. I'll be left with y squared plus 10y. That's a little easier to do in my head. And then that equals negative 2,210. Now, to complete the square, 16 divided by 2 is 8. 8 squared is 64. So I'm going to add 64. Now be careful though. When I'm adding 64 here, this 64 is in the inside of this parentheses. So really what I've added is 32 times 64. Okay? That's important because when I go to balance it on the right-hand side, I'm not going to say plus 64. I'm going to say plus 32 times 64, right? Whatever that is. 32 times 64 is 2,048. So I'm really going to add 2,048, okay, to balance that one. In this group, 10 divided by 2 is 5. 5 squared is 25. So I'm going to add 25 to complete the square on that group. But really, what I've added is 18 times 25, right? So to balance it, on the right-hand side, I need to add 18 times 25, which is 450. Okay, let's see what we get now. I've got 32 times x, this one's going to be x minus 8 squared, plus 18 times, this one's going to be y plus 5 squared, and this equals negative 2210 plus 2048 plus 450 is 288. Now at this point, this isn't really looking like any of the conic sections that we know and love. I'm squaring both the x's and the y's, so I know it's not a parabola. And I have a plus sign here in the middle, so I have a feeling that this is not a hyperbola. I think this is an ellipse. What we need to do to get it to look like an ellipse is that the right-hand side needs to be 1. Now there are a couple ways that you can get the right-hand side to be 1. One way you could do it would be to subtract 287 from both sides. But if you do that, the left-hand side is still not going to quite be in graphing form, right? Because graphing form looks like, x minus h squared over m squared plus y minus k squared over b squared. So we know that we need to be dividing these two groups by something, which tells me that maybe a better way to get 1 on this side would be to just divide through by 288. So that's what I'm going to do. And then these fractions will reduce, right? So let's see. 32 over 288 is really 1/9. So really this is x minus 8 squared over 9. And then 18 over 288 is really 1/16. So this is y plus 5 squared over 16, right? When you reduce the fractions. And this equals 1. So now we can see really clearly that, okay, yeah, this thing is an ellipse, right? It's an ellipse with center 8, -5. M is 3, N is 4. Okay, so let's see what we've got. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. M is 3, so I'm going to move left and right 3. 1, 2, 3. 1, 2, 3. And N is 4, so I'm going to move up and down 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So there we go. There's the ellipse. Okay, let's do another one. Part C. Notice that on part C, I don't even have an x squared. I only have a y squared, which kind of tells me right off the bat this must be some kind of parabola, right? But if I want to write this thing in standard graph, or not in standard form, if I want to write it in graphing form, then I need to complete the square on my y group. Okay, so I'm going to group the y terms together. So I'm going to have y squared plus 10y, and then I'm going to leave myself some space. The other terms I'm just going to move over to the other side because I'm not completing the square on them. So I'm going to move x over by adding x to the other side, and the 16 over by subtracting 16. Now, we've completed the square on this one already, right? Half of 10 is 5, and 5 squared is 25. I don't have any coefficient out here, so I really am just adding 25 in order to balance that on the left-hand side. I get y plus 5 squared equals x plus 9, I believe. Okay. I think we're actually used to seeing this the other way around, right? Usually we write this as x plus 9 equals y plus 5 squared. Okay. But it's pretty clear now. Okay, so this is a parabola. The vertex is -9, -5. And this thing opens, well, x came first, so it opens along the x-axis. And a is positive, so it's going to open right. So let's see. -9, 1, 2, 3, 4, 5, 6, 7, 8, 9, -5, 1, 2, 3, 4, and 5. There's the vertex. And then this thing opens right, so it's going to look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. You don't have to get this many points. As long as you get these first 5, I'll be happy. But 9, and then it would be 16, 9, 10, 11, 12, 13, 14, 15, 16. And then 25 is going to be off the page, but that's that. Okay, so So that's what that parabola looks like. Okay, do I have an example of a hyperbola on the next page, I wonder? Yes, I must, right? I've got one more example. It's got to be a hyperbola, right? I mean, it's got to be. Well, let's do it. Okay, so I'm going to, this time I have an x squared and a y squared, so I'm going to have to group my x's and my y's. Well, this is kind of interesting. So here's how I'm going to do it. I'm going to say plus negative 9y squared plus 54y. And then the 17 I'm going to move over to the other side, right, by adding it over to the other side. Now let's do like we did with the ellipse and factor out our leading coefficients, right? So I'm going to have 4 times x squared plus 10x, leave some room. I'm going to factor out a negative 9. I'll have y squared minus 6y, leave yourself some room. Okay. We've done this one so many times, right? We know that we're going to add 5 to complete the square, or 25 to complete the square on that group, except that we're multiplying it by 4, so really we added 100 on the left-hand side. So we've got to add 100 on the right-hand side. Here, 6 divided by 2 is 3, and 3 squared is 9, so we would add 9 to complete the square on this group. But I'm really adding, or rather I'm really subtracting an 81, right? So I have to subtract 81 on the left-hand side. Okay, so be very careful, right? Make sure that you're getting, make sure that you're balancing things on the left and right-hand sides correctly. Pay attention to the signs and everything else. Okay, so now this is 4 times x plus 5 squared minus 9 times y minus 3 squared equals 17 plus 100 minus 81 is 36. Oh, look at that. These problems have all been rigged so that they work out nicely. They don't have to be, though. You might come across some problems where in the homework where things are a little messier. But anyway, this one we can do in our head for sure. This is x plus 5 squared over 9 minus y minus 3 squared over 4 equals 1. And there we go, hyperbola, right? It's a hyperbola for sure. This is a hyperbola. The center is negative 5, 3. M is 3, N is 2. And this one's going to open left and right. So let's graph it. Center is negative 5, 1, 2, 3, 4, 5, 3, 1, 2, 3. M is 3, 1, 2, 3, 1, 2, 3. N is 2, 1, 2, 1, 2. And then remember, unlike an ellipse, we're not going to connect this with a curve. We're going to draw a box now. Then we're going to draw the diagonals of the box. These are the asymptotes of our hyperbola. And then this hyperbola opens left and right. So my vertices are there. Well, try to do better than me. You should be getting closer and closer to that asymptote. And there. Okay. So that's that, right? That's what that one looks like. Okay. So now that we've practiced how to graph conic sections when they're given to us in this kind of standard form rather than the graphing form, let's talk about how to tell what you've got on your hands just by looking at it before you go to complete the square. So, first of all, in this section we're assuming that b is equal to 0, right? So again, we're looking at this equation: ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, right? So this is the equation we're looking at. Now, if b is 0, so if this term is gone, and if either A is 0 or C is 0 but not both, then the conic section is a parabola, right? Because if let's say that A is 0, so then you're going to have a y squared but no x squared. Or if C is 0, then you're going to have an x squared but no y squared. And in both of those cases, right, those are parabolas, as we've discussed in the past. Okay, so if one of these things is 0, you've got a parabola. Now, if A and C are both positive or both negative, so if A and C have the same sign, then since you're going to be adding these things, or you could factor out the negative and then you would still be adding A plus C, right? So, or ax squared plus cy squared. So in either case, that means that you've got an ellipse, right? Because in order for you to have a hyperbola, you have to be subtracting the x group from the y group, or the y group from the x group, which means that A and C would have to have different signs. So if A and C have the same sign, then the conic section is an ellipse. And more specifically, if A and C are exactly the same number, then the ellipse is really a circle. And then finally, if A and C have different signs, then you've got a hyperbola. Okay. Now, all of this is kind of loosely speaking, because the fact is that you could have degenerate cases, as we discussed on the previous page, right? So you could have values for A, C, D, E, and F that together really don't make any sense at all, and they give you some kind of point or line or just some like equation that can't possibly be true or something, right? So that could happen, right? You could have degenerate cases, but assuming that the values for A, C, D, E, and F all give you an actual conic section as a result, then these statements are true. So these are not like super precise. So I guess what I'm trying to say is that these are not super precise, but they do give you some intuition as to what you can expect to happen before you go to complete the square. So with that in mind, just looking at these kind of standard forms rather than the graphing forms, and rather than trying to complete the square, let's see if we can just identify what the conic section is just by looking at these equations. Okay. So looking at part A, I have both an x squared and a y squared. So for sure this is not a parabola. The signs of x squared and y squared are the same, right? They're both positive. So I know that this is not a hyperbola. Now the coefficients of x squared and y squared are the same number. So this must be a circle, right? This is a circle. That's really all I can say about it for now. It's hard to tell what the center and radius are without completing the square. But I know that it's going to be a circle. It's either a degenerate conic or it's a circle. Okay. Part B. I've got an x squared but no y squared. So this is a parabola. Right off the bat, I can tell it's going to be a parabola. And in fact, since I've got an x squared, no y squared, I know that I'm going to be able to get this to look something like y equals x squared. It's going to look like the format y equals x squared. So I can even say a little bit more. I can say that this thing is going to open up or down. Okay, it's going to either open up or down. Okay. I'm looking at part C. I've got an x squared and a y squared, so it's not a parabola. The signs of my x squared and y squared are different, so this must be a hyperbola. And again, I can kind of intuit which way this is going to open, because it's the x squared that's negative and the y squared that's positive. So when I go to rewrite this, it's going to look like, y squared minus x squared, which means this thing is going to open up and down. Okay. Anyway, determining which way the thing's open isn't really necessary. We were only asked to identify the conic, and this is definitely a hyperbola. So go ahead and pause the video, see if you can do the next 3 on your own. Here are my solutions. This one's got to be a parabola. This one's got to be an ellipse. And this one's got to be a hyperbola. So that's that. Okay. So identifying conic sections is really not too difficult if b equals 0. If b does not equal 0, then it's a little bit more difficult to tell what's going on. And again, we're going to talk about this in the next section. Okay, but for now, we can use a tool called the discriminant to tell what kind of conic section we have. And the discriminant may be something kind of familiar to you. If you're looking at the conic section, right, or the conic section, if you're looking at the quadratic formula, x equals negative b plus or minus square root of b squared minus 4ac over 2a, the stuff inside of the square root is called the discriminant. When you're dealing with quadratic equations, the discriminant tells you the number and type of solutions that you can expect to have, right? So if b squared minus 4ac is positive, then you know that you're going to have two real solutions. If b squared minus 4ac equals 0, then you know you're going to have one real solution. And then if b squared minus 4ac is less than 0, then you know that you have two non-real solutions, right? So that b squared minus 4ac is called the discriminant. And so it's something that you may have come across in your previous algebra experiences. Notice that the discriminant for a conic section is the same. It's b squared minus 4ac. And the cases that we consider are also the same, right? We look at when the discriminant is 0, when it's less than 0, and when it's greater than 0. But this time the information it's giving us is what kind of conic section we can expect to have based on the discriminant, right? So if the discriminant is 0, then the conic section is a parabola. If it's negative, then the conic section is an ellipse. And if it's positive, then the conic section is a hyperbola. Now, I'm not going to prove this result to you, but here's a link to a proof of this fact if you're interested. So you can click on this link and follow along with the proof if you want. What I do want to do is I want to take you to Desmos and kind of show you some conic sections and their corresponding discriminants, because I think it's really kind of fun and interesting. So let's take a look at Desmos. Okay, so here we have our general form of our conic section, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. And I've created little sliders for a, b, c, d, e, and f so that we can change those values if we want. And then down here, I have the discriminant, b squared minus 4ac. So you can see that right now the discriminant is negative 3, and sure enough, we have an ellipse, right? We have an ellipse. If I make b equal to 0, that might be even better, so it's easier to tell what's going on. Again, so if I make b equal to 0, b squared minus 4ac, in this case is negative 4. Again, you've got an ellipse. I think this one is actually a circle, right? Because a and c are the exact same number. And I'm just going to let a go for a while. Ooh, okay. So notice that when a is negative, this makes the discriminant a positive number, and sure enough, you get a hyperbola, right? So that's kind of interesting. I'm going to let this continue to go. You still have a hyperbola. At some point, it kind of, so it's an ellipse, and then it turns into a parabola for a second, right? When a equals 0, the discriminant is equal to 0, and so you get this parabola, right? Sure enough. It's kind of interesting. It's like the ellipse eventually gets so big that it can't close, and it just turns into a parabola, right? And then it starts to get even bigger, and so like a second side of it appears, right? So it really becomes a hyperbola, I guess. That's kind of cool, though. I think it's fun. Okay. We could do the same thing with C. Maybe I'll let A be 1 again. You can do the same thing with C and kind of play around with it. It just gets flatter. But it's still an ellipse, right? Because look at your discriminant, right? Your discriminant's still negative. The discriminant eventually, though, is going to become 0. So you get a parabola. And then the discriminant will become positive and you get a hyperbola. Oh, and the hyperbola changes direction. That's really cool. I think that's fun. We can do the same thing with these other things and see how they affect stuff. notice that the discriminant is just b squared minus 4ac. And so you can see that changing the value of d doesn't change the conic section. This is still just a hyperbola regardless, right? Same thing with e. If I change e around, I still have a hyperbola. I mean, it changes the conic, it changes the graph, but it doesn't change what kind of conic section you have, right? Same thing with f, right? This will kind of change things a little bit, but you're still going to have a hyperbola, right? If, on the other hand, see over here it's degenerate, right? Over here you get an ellipse because your discriminant's negative, right? Ellipse is still, but if I change c, then potentially we can change what kind of conic section we have altogether, right? That's kind of interesting. Anyway, and then just for fun, I'm just going to press play on all of these and just see what chaos ensues. It's kind of funny. You could let b go as well, and then you're going to start to see things tip over and do all kinds of crazy cool stuff. Oh, wow. I could stare at this all day. Anyway, that's it for that. I gave away what 5.4 is all about. Where am I? There I am. Okay. So hopefully, looking at that animation in Desmos kind of convinces you that, yeah, this discriminant really does tell us what we've got going on, even if b is present. So if your b term is missing, you can tell what you have without having to look at the discriminant. But if b is there, right, if b is not equal to 0, then the discriminant is going to be how you identify the conic section. Okay. I've got a train coming by my house, so let me pause this for a sec. All right. The train is still passing by, but it stopped honking its horn. Okay, let's just practice using the discriminant to identify the conic section, right? So the discriminant, maybe I shouldn't use d because d is a letter that we already use in our conic section, right? So I'll just write out b squared minus 4ac. For this one would be, so b would be square root of 7, right? So it would be root 7 squared minus 4 times 2 times 5. Just be careful, right? b is the coefficient on your xy term, a is the coefficient on your x squared term, and c is the coefficient on your y squared term. So in this case we get 7 minus 20 times 2 minus 40. This is a negative number. It doesn't even matter really what the answer is. You know that it's negative. And when your discriminant is negative, you've got an ellipse. So this must be an ellipse. What about this one? So let's see. B squared minus 4 times a times c. Now be careful. C is 0, right? Because you have a 0y squared. So c is 0 in this one. This is going to be a positive 16, which is greater than 0. And when your discriminant is greater than 0, you've got a hyperbola, right? So this must be a hyperbola. Okay. Now you might be thinking, well, wait a second. If we're missing the y squared term, we only have an x squared but no y squared. Doesn't that usually mean that we have a parabola? And you're right, it does usually mean that we have a parabola if the xy term is missing. But see, when you throw the xy term into the mix, that messes up our intuition pretty badly, right? And again, we're going to talk about that in the next section. Let's look at this one. So b squared minus 4 times a times c. That's 36 minus 36. Oh, so that's 0. Okay, so when you've got when your discriminant is equal to 0, that's when you have a parabola. Okay, so there you go. That's how we determine what kind of conic section we have. Now the question is, what does the bxy term do to how the graph looks? Well, we'll see in the next section. Looking at that animation in Desmos, you probably have some idea, right, that it's going to rotate things a little bit. But that's all I'm going to say for now. I'll see you in the next section.